So hello everyone. In the last lecture I discussed about chemical potential. Now today I will discuss about the system of variable composition. And in this lecture I will try to cover three topics, that is fundamental equations for the system of variable composition, molar and partial molar quantity, and the last one is the additivity rule and the Gibbs-Duhem equation. Okay, we'll start one by one. So the first topic is the fundamental equation of thermodynamics for a system of variable composition, right? The first thing we should know that what is the system of variable composition. Actually, there are some systems having leak-proof boundary and which is adiabatic in nature also. So definitely matter and energy can't be transferred through this boundary, but chemical reaction can occur. So the composition of the species within the system will also vary. Therefore, these systems are known as the system of variable composition. Therefore, the law of thermodynamics, which is applicable to the open system, is equally applicable to the system of variable composition. Now, we'll try to derive the fundamental equations, okay, for the system of variable composition. For closed system, what we know? For closed system, we know that G is a function of T and P. But whenever we are considering the system of variable composition, then we need to consider G is a function of temperature, pressure, and also the number of moles of the components in the mixture, right? Therefore, the expression is written as G is a function of T, P, N1, N2, Ni. That is the N1, N2, these are the number of moles of each component, right? So G is a state function we know, and D is an exact differential. Therefore, we can write that del G del T at constant P N1 N2, del G del P at constant T N1 N2, del G del N1 at constant P T N2, del G del N2 P T N1, and finally del G del Ni. This is the number of moles of ith species at constant Tp Nj, where Nj, this is important, Nj is not equal to I, and J is like 1, 2, 3, this, okay. So what we get? Minus SdT, we know this from the uh, classical thermodynamics. This is VdP, and this is like del G del Ni at constant Pt Nj. Now this expression we have derived in the last class, because this is equal to mu y. So overall the equation comes as minus SdT plus VdP plus summation I mu y dni. So this is one equation, fundamental equation based on considering Gibbs free energy, right? Suppose we want to derive fundamental equation in terms of enthalpy, then what we'll do? So we'll do like we know that H equal to G plus Ts. Now dH equal to dg plus tds plus sdt. Okay, now what we get in the last equation? What we get in the last equation is del G equal to minus sdt plus vdp plus I mu I dni plus tds plus sdt, right? So these two cancel out. So overall what we'll get? tds vdp plus mu I dni, right? Right. So this is the second equation. Similarly, we can derive du equal to tds minus pdv plus mu I dni, third equation, and dA equal to minus sdt minus pdv plus summation I mu I dni, right? So overall 4 fundamental equations can be derived for a system of variable composition. Now one thing we'll see that if for this second equation, let's say if S and P is constant, then what we'll get? Del H del Ni at constant P S Nj not equal to Ni equal to mu I. Similarly here also del U del Ni at constant S V Nj not equal to I equal to mu I. In terms of, suppose if you write the chemical potential in terms of Helmholtz energy, what will write that del A del Ni at constant T V Nj not equal to Ni equal to mu I, right? So from these 4 fundamental equation we'll get four expression of chemical potential, right? So among these 4 expression of chemical potential, we are familiar in expressing chemical potential in terms of molar Gibbs free energy, because most of the chemical reaction is taking place at constant temperature and pressure, right? So this is the most common form while representing chemical potential, but chemical potential can be represented by these 3 equations also. Okay. So now we are coming to the next topic of discussion, that is the molar quantity and partial molar quantity. Look, for a system of variable composition, number of mole is variable, right? Therefore, it is a common practice to define any extensive property per mole of a substance. Okay. So suppose E is an extensive property, then if and n is the number of mole, then we can write that E by n is the molar quantity and it is represented as E bar. When bar is given, that means it is defining the molar quantity, right? In other words, we can write that increase of E when when n mole substance is added, when one mole substance is added at a constant temperature and pressure, then molar quantity is defined as dE dNi at constant T and P. Okay. So whenever other two parameters are constant, then molar quantity is written in the form of del E by del N. But in normal condition, where temperature pressure is not constant, if you want to represent a molar quantity of an extensive property, then it is like E by N simply. Okay. So this is the molar quantity concept. Now if we want to know about the partial molar quantity, basically when we consider a homogeneous solution, a solution contains several components, right? So if we want to know the partial molar value of an extensive property E for a particular species within the solution, okay, then we'll use this partial molar quantity concept. Okay, we'll explain. Suppose E, we want to define the partial molar value of an extensive property E in a homogeneous solution of ith species, okay, of ith species. Then what we'll write? We'll write that E bar equal to del E by del Ni by at constant temperature, pressure. So while we are defining the partial molar quantity of a extensive property of a particular species, then the number of moles of the other species should be constant, right? So this is the concept of partial molar quantity, right? Let's say we want to represent the partial molar entropy, then how we will write? So Si bar equal to del Si Ni at constant T P Nj is not equal to Ni, right? If we want to write the partial molar volume, del V del Ni at constant T P Nj not equal to Ni, right? Simply. Now from these two expressions, this one and this one, we'll derive two important derivations can be done, okay. like what we'll get, uh, SI bar equal to dSi by dNi constant T P N J not equal to Ni. Now we can write that dNi is minus dg d sorry dt, okay, at constant P and N in J. So T P N J not equal to Ni. So based on the Euler's theorem of reciprocity, what we can get is dg by dni at T P N J not equal to Ni equal to P N J not Ni. Okay. So overall, what it will come, d mu I dt minus at constant P N J not equal to I, right? Similarly, what do we know that similarly Vi equal to dvi dni at constant Tpnj not equal to ni, we can write that dg dp at constant T nj not equal to ni. So based on the Euler's theorem of reciprocity, what we'll get that d mu I dp at constant T not equal to ei. So right, and this is Vi bar. So these two equations are very important in terms of examination, because sometimes these expressions has to be derived in the examination. Okay. Now some so once we have understood about the molar quantity and partial molar quantity, then few points we have to remember. The first point is the molar volume. When molar volume and partial molar volumes are equal, then there will be no change in the volume when pure substances are mixed. When pure substances are mixed, okay, that is delta mix V equal to 0. Similarly, when the molar enthalpy and molar partial molar enthalpy are equal, then delta mix H equal to 0. So what does it actually mean? Let's say two components, one component having the number of moles of N1 and molar volume V1 star, other component N2 molar volume V2 star bar. Okay, so this V1 star bar and V2 star bar defines the molar volume and the pure state. So before mixing, total volume will be these two, sum of these two. Now after mixing, the volume becomes V1 bar, and these two become, this becomes V2 bar. So total volume V1 n1 v1 bar, n2 v2 bar. So total becomes v total is defined as n1 v1 bar plus n2 v2 bar. Now delta mix v equal to v dash minus v, right? If it is ideal, that means v dash minus v equal to 0. V dash minus v is equal to 0 means, what does it mean? That partial molar volume and molar volume both are equal. Similarly, for delta mix H equal to 0 for ideal solution, and this can be calculated once we know the heat of absorption at the constant pressure. Okay. Now if these two, like that is delta mix V and delta mix H are 0, then a solution is considered as an ideal solution. Otherwise the solution is non-ideal solution. From molecular point of view, a mixture of AB will be ideal if AA, BB and AB, all the interactions are identical. If all interactions are identical, then only we can say that the solution is ideal, the mixture is ideal. Now what is the concept is what is the ideally dilute solution? Ideally dilute solution, right? Ideally dilute solution is nothing but a non-ideal solution which is extremely dilute condition, that is a very dilute non-ideal solution. Okay. And the last point is, for an ideal or ideally dilute solution, delta mix S is greater than 0 or delta mix H is less than 0. That is, ideal gas mixing can take place spontaneously. We will derive these two, that is delta mix S greater than 0 and delta mix G less than 0 in the later classes. Okay. So for the time being, we should know the last point. Okay. Okay. Now coming to a specific example. So you can try this by your own. Otherwise, we'll solve this example in the later classes. Okay. Here we have given the weight of the two components, like two components, water and ethanol. Their molar volume of the pure substances given are given, and partial molar volume of the two components are given. Now we have to define delta mix V. That is our task. You just try by your own. In the later class, I will solve it. Now coming to the additivity rule. Okay. Now this additivity rule is important to derive Gibbs to Hem equation. Sometimes in examination, this Gibbs to Hem equations we need to derive, right? Especially in UPSC GSI, there is one physical chemistry descriptive paper. They sometimes asked to derive this Gibbs to Hem equation. Now, what is this additivity rule? First, we need to know that. So, for an open system, we know that dg equal to minus sdt plus vdp plus mu I d ni. Okay. So you see that all the time the fundamental equation is this only. Okay. From this equation we are deriving the other equations. Okay. Now initially the system, the container is vacant. Now Ni is the number of Ni number of moles of the ith substance is added. Therefore the Gibbs free energy is no longer V0, it becomes G. So if we want to integrate the equation, that initially it is 0, now it becomes g dg equal to, and here we have considered that T and P to be constant, while ni number of moles is added, right? So I integration, initially system is system is vacant, ni is added, mu ni dni. Okay, here one thing also we need to remember that mu I chemical potential is not changing during this process. Now after integration, what we will get, that gi equal to I mu I dni. Okay, for any extensive property E, we can write that mu I ei bar. Okay, so we can replace this E I by other extensive properties like SI, molar entropy, molar volume, molar Helmholtz energy, etc. So this is the generalized form of the additivity rule. Okay, now we are using this additivity rule in order to derive this Gibbs-Duhem equation. So what we know, that for an open system, minus SDT plus VDP plus mu dni. Again we'll start with the same equation. Now at constant temperature and pressure, what we'll get, mu dni, right? This is equation number 1. Now from additivity rule, we get that mu ni, right, equal to dni plus I ni d mu I. Okay, this is equation number 2. Okay, now from equation 1 and 2, what we'll get, that mu I dni equal to mu I dni plus ni d mu I. These two cancel out. What we'll get is ni d mu I equal to 0. For a binary solution, we can write that n1 d mu 1 plus n2 d mu 2 equal to 0, right? Dividing both sides by total number of moles, that is n1 plus n2, we can write that x1 d mu 1 plus x2 0. So equation number 3, equation number 4. These 3 and 4 are the two forms of Gibbs-Duhem equation. Okay. Now what is the outcome? What is the significance of this Gibbs-Duhem equation? n1 by n2 minus d mu 1 equal to d mu 2. That is, for a binary solution, if the chemical potential of a particular species increases, that means the chemical potential of the other species will definitely decrease. That is, if d mu1 is positive, that is chemical potential of the first species increases, then from the equation we know that d mu2 is negative, and vice versa. Again, if d mu1 is negative, then d mu2 is positive. So this is the significance of the Gibbs-Duhem equation. So we'll conclude here and see you in the next video. Thank you.